Hello and welcome again to the radiation heat transfer lecture series. So we are almost at the verge of the end of the lecture series. We will be taking at the most 3 to 4 lectures. So I will be covering one more topic, that is the radiation in participating media, and if I get the time then I will be solving some problems. I will be solving at least one problem from the participating media, and other than that also what I have taught already, from that also I will try to solve one more or maybe 2 3 more problems. So without any delay, let us start. I almost forgot that what is the lecture number, so let me continue without that. So here now I will be starting radiation in participating media. So just for the recap, actually I am recording the lecture after so many days. I think I have covered the method of radiation network, right, at how to do the problems and all. Okay, so I have almost covered everything, but honestly this, like the conduction series, I mean, in the conduction series, I can guarantee you, I can make you from zero to hero. But this radiation series is for actually some intermediate things. I have talked about the things from the very basics, but still, I have not gone into very advanced things. There are so many things in conduction also. I could have covered so many things, but still, radiation is a bit of intermediate course. Okay, neither it is very basic nor it is very advanced. So radiation in participating media. Okay, so up till now we have considered that if we have maybe a medium, okay, so this is a control volume maybe, and you will consider that some radiation energy is going like this. Okay, now if this has the intensity I, so when it will be coming out from this control volume, what would be the intensity? I will term it as In dash. Now this media if this media is a non participating one, okay, for example, maybe you are driving through a road, okay, so you are driving through a road and you are seeing that no car and nothing is there, okay, so for you to drive is very easy, and the energy and the speed with which you started driving through the road, at the end of the road also you will maintain the same speed, okay, because in between you haven't faced any kind of obstacle like any other car, any other human, any other animal, or anything else. So that is why when you are going into the path, the speed was s, and when you are coming out of the path, the speed is still s. Okay, and in the whole journey, the speed has not decreased or increased from s, because for you the comfortable speed is s. Okay, so that is the concept of non-participating media. If the media is non-participating, then we will be having In dash is equal to In. Okay, I eta. Eta is nothing but that the I is dependent on the wavelength. Okay, so lambda is wavelength and eta is wave number. So you can actually write lambda instead of eta also. Now, if the media is participating, if the media is participating, okay, so then what can happen? So again you are driving through this road, in between this road when you are here, another car is here, and that is why you were like, okay, now I need to slow down, but after you overtook the car, then again you are like, okay, now I can speed up. So like that your speed has been decreased and also has been increased throughout the journey, and that is why this speed, that is this outgoing speed s dash, will either be less or be greater than s. We cannot say like that. Okay. So because in the journey, through the journey, in the path, you have decreased your speed, also you have increased your speed. Okay. So in the participating media, the funda is that my I lambda dash is not equal to in. Okay. So these are the basic difference between a participating and a non-participating media. Okay. So now my question is that how this I eta, okay, how I am writing this, how I eta, okay, will be increased or decreased. Okay. So how this can happen? So what is I eta? This is nothing but the radiation intensity. Okay, radiation intensity. That thing, that is the radiation energy per unit area normal to the rays, per unit solid angle, per unit wavelength, and all okay, that was the concept. So this is the radiation intensity. So radiation intensity is nothing but energy, radiation energy. So if I have to increase or decrease the radiation intensity, that means, okay, if I have to increase that, okay, now why this is coming as a black, I mean it's coming as white. Okay, just adjust. Okay, the page has turned suddenly from black to white. Now in, so if I have to increase this in, then what I have to do? If I have to increase in, then my option is I have to add energy, right? Add energy, or more specifically add radiation energy. And if I need to decrease the in, I need to remove energy. As simple as that, right? Now tell me, how can I add energy? So I can add energy by, okay, okay, I will talk it later. I will talk about it later, but now uh, in terms of technical language, this called uh, augmentation augmentation of the radiation intensity, and this called the attenuation. Okay. So our basic principle or our basic objective is to find that how much is in, so how much is the increase in I and how much is the decrease in I, and thusly how much is the total change in I when it is traveling through a participating media. So for all the things we will be considering something like this, that we have a distance s, or maybe we have something like this, okay, a cylindrical CV, okay, and this is our ds, chota wala s. Okay, now at this point, so this is situated at s, this CV, so this is s and this is actually s plus ds. Clear? Now at this point, this I eta s, this is the radiation intensity. So some radiation ray is passing through this cylindrical control volume. Now I want to know that what is this? This will be what? Okay, this will be what? And honestly, I should have written I eta s plus ds, okay, comma t plus dt, because I mean if you have to travel from you have to travel from here to here, then it will take some time, right? So and like that the radiation energy will also take some time, or the radiation ray will also take some time. Okay, but we will see. And moreover, this ds is nothing but c into dt. C is the velocity with which radiation ray is traveling. And we will see that what can we do about this time. Okay, but for now we are interested on the dependence on this s. Okay, so firstly let us see that how attenuation occurs. Okay, so firstly we will be seeing the attenuation. Okay, I have already told you that attenuation means decrease. Okay, so now attenuation can happen by two ways. The first is, okay, let me do it like this. Attenuation can happen like this. The first is the absorption. So as the name suggests that when the radiation ray is passing through the media, the energy from the radiation ray will be absorbed by the particles of the participating media. Okay, so maybe I will be writing that here, that energy from the ray is absorbed by the media. Okay, another is outscattering. So here energy will be scattered out from the ray during traveling through the media. Okay, so it is so scattering is actually very much uh, I mean random. So if this is my CV, okay, and if something is going, okay, like this, so scattering will be like this, okay, so it will be going out from the CV, and whatever is coming, that will be this minus this, okay, so this is actually scattering. Okay, and absorption is the energy will be remaining in that control volume. I mean the particle which were there inside the control volume, okay, so they will absorb the energy, but scattering is the energy will be most probably it can stay in the control volume because the scattered energy will be also get absorbed by the particle. It can also go out of the control volume. Okay, so that is the difference between absorption and scattering. Okay, so now let us go for the absorption. So attenuation by absorption. Okay, So it says that the change in the radiation intensity at a particular position S is actually proportional to the radiation intensity at that position. Okay, and also it is proportional to the length ds through which it is traveling. So if we now bring a constant of proportionality, now see, attenuation means it will be decreasing, right? So I will be now having kn this into this. Okay, so this kn is called linear absorption coefficient. Okay, linear absorption coefficient. Okay, and just for the information, it can also be written like this: kn rho ins rho ds. It can also be written as minus kn p ins pds. Okay, so this rho and p are the density and pressure of the media, and this is called mass mass absorption coefficient, and this is called pressure absorption coefficient. So you don't need to just remember these things, okay, but you need to remember at least this one. Okay, so this formula is very important. Okay, this one. Okay, so this formula is very important. Okay, so I can name it by this, this equation will be called A, capital A. Okay, so this was attenuation. Okay, so the very important thing, there are some assumptions. Okay, so I will write here actually, maybe here. The assumptions are very important. Okay, so throughout this course, when I will be teaching this participating media, the assumptions are non polarizing media. Okay, and local thermal equilibrium is there for all the points. Clear? And the final is the refractive index Ri is constant throughout. Okay, now these assumptions has got some significance. I will only talk about the significance of the LTE, local thermal equilibrium, that is LTE, but for the time being I don't have the time to discuss about the other two assumptions. Okay, for this reasons I am just telling all the times that this course is not very advanced one, this is an intermediate one. So attenuation by absorption. Now attenuation by what? Attenuation by scattering, or to be more specific, out scattering, because there will be in scattering. So I think you are intelligent enough to guess that if out scattering is causing attenuation, then in scattering will cause augmentation. Okay, so attenuation by out scattering, it is the same thing, just the coefficient will be changed, that is din. Okay, that is a function of s, the position. Okay, and okay, so to be very specific I should write, अरे पेज को क्या हो गया? Okay, so this can have a subscript abs, that is absorb, din due to absorb, and this is din due to scattering SCA. Okay, so this is equal to sigma ns, okay, into INS, not N, these are eta, and into ds. So this is again nothing but the scattering coefficient or outscattering coefficient. Obviously there will be a minus outscattering coefficient. Okay, so this minus I will be giving with a black color. Again, this is also a very much uh, important equation, so I name this as B. Okay, so now I have given you two very important equations. Okay, so now let us see that for a non-scattering media. Okay, so for a non-scattering media, or even if I do have a scattering media, so total attenuation, if I have to write the total attenuation, so this is also only due to absorption, and outscattering, right, and outscattering. So this I can write as, this is a function of S is equal to, okay, minus Kn INS ds minus sigma ns, okay, INS ds. So I can take common and I can write minus beta n, okay, forgive me that I am just uttering n, these are eta. So where this beta n is equal to nothing but k eta plus sigma eta s. Okay. So now if I assume that this beta eta is not a function of s, then I can write that d I eta s by I eta s is equal to minus beta eta ds, right, and therefore I can integrate it from in0 to ins, and this as from 0 to s. So what is in0? So I have already shown you the control volume like this, right? Yeah. I have already shown you the control volume like this. So here this point is s equal to 0, this is, and this is actually ds. I mean, so I mean s equal to 0 means the entry of the control volume, nothing more. Okay, so this will be what I can write directly this as I eta s is equal to I eta 0 e to the power minus this one. Okay, now this is also written as tau eta. Okay, so this tau eta has a name, has a separate name, and this is called optical thickness. Optical thickness. So you can see the unit of this tau will be length, the unit of the length, because beta is unitless. Okay, now what is the significance of this term optical thickness? You see, the more is the tau eta, the lesser will be this I eta s. So it is actually the radiation ray is traveling through ds or traveling through s. But from this equation, it is apparently seeming that this tau eta is like a apparent distance which is affecting this I eta s. So that is the concept of optical thickness. That means if someone asks you that how much this medium is optically thick, okay, so then you have to see that how much I eta is decreasing. Okay, so you are getting some incoming uh, radiation intensity, that is I eta 0, but when the radiation ray is leaving the control volume, then how much is this I eta s, uh, I mean which is leaving, that you need to answer that question, that how much this medium is optically thick. So that will not depend on the actual thickness S, but that will depend on this tau eta. That is why it is called optical thickness. Okay. So now, if I simplify that, for non-scattering media, okay, media, okay, I should write medium because it is plural. So sigma eta s will be 0, that means beta eta will be just k eta, that is the absorption coefficient, and that means the optical thickness will be minus k eta s from 0 to s. Now for this case, that is for a non-scattering media, okay, you can see that my I eta s by I eta naught is equal to nothing but e to the power minus tau eta. Okay, so now can you tell me that what is the definition of absorptivity? Okay, so here the spectral absorptivity of the medium, okay, and that is defined by how much is incoming and how much is absorbed. So absorbed is eta naught, I eta naught minus I eta s. So that is nothing but your 1 minus this one. So this is your alpha eta. Okay, and we also know that my transmissivity, okay, transmissivity, so if I write this as directly, so spectral transmissivity, so that is equal to directly how much is outgoing from the medium and how much was supplied to the medium, and that will be equal to directly there will be minus this one. Okay, and if the Kirchhoff's law is valid, then my alpha eta will be epsilon eta, okay, is equal to this one. So all these things were valid for a non-scattering media. Okay, so now let us see. Okay, fine, and always keep in mind these assumptions: non-polarizing media, local thermal equilibrium. Actually just now this assumption, local thermal equilibrium, will be applicable. See, so we have completed the attenuation. Now I will talk about the augmentation. Okay, so the augmentation, and what does this mean? That is the addition of energy, okay, or the, I should write increase, because for attenuation I wrote decrease, right? So likewise for augmentation, okay, for augmentation again, we are having two ways. One is in scattering. Now I think you can at least guess, that is the energy is scattered inside the control volume. If this is my control volume, then energy is scattered inside randomly. Okay. Now among some of this energy, among these radiation rays which are being scattered inside, some energy will get absorbed by the molecules inside the CV and some will be being added with the ray that is incoming through this CV. So in scattering and emission. Now this is something very confusing, because emission means something is being emitted. So how can it be added? So emission means, I should be very precise, that emission, okay, by the medium. So energy is being emitted from the medium or by the medium, and that energy is being added to the ray. Okay. So now here I will be taking that assumption. So firstly let me talk about the augmentation by emission. Okay. Augmentation by emission. So fundamentally this is directly written as di eta, there will be a subscript emission maybe, that is equal to j eta, that is a function of s, okay, or let us not consider it a function of s, into ds. Clear? Now if local thermal equilibrium is valid, that is if LTE is valid, okay, then this j eta becomes k eta into IB eta. Okay. So there is a formal proof for this, but I don't have the time to go through that. I will be just giving you the informal intuition. So for emission, when I taught you the emissivity thing, okay, so we know that the energy emitted from a surface S at a temperature T is equal to epsilon S, that is the emissivity of the S, into the what? Into sigma T to the power 4, that is epsilon S IB at the temperature T. And we know that if the Kirchhoff's law is valid, then this emissivity of S is becomes alpha S for a diffuse gray surface. So this is valid if the Kirchhoff's law is valid, right? So that means this emission from a surface becomes the absorptivity into the black body radiation, black body emission. So I should write EB here, EBT. Okay, so this is also EBT, not IBT. Okay, so this EST is equal to absorptivity into the black body emission if only the Kirchhoff's law is valid and if the surface is diffuse and gray, right? Likewise, see here I am getting that my, so if I put this, okay, if I put this Jn, so then I will get di eta emission is equal to Kn, now IBN, but that will be a function of S because the temperature can vary into S, into ds. Now you see, that means this part is governing that how much emission will happen, that much emitted energy will be added to the ray. But this emission is what? The absorptivity, the absorption coefficient into this black body intensity at that position. So can you see the analogy between this and this? This Kn is analogous to alpha S, this IBN is analogous to EBT. This is a very rough intuitive analogy, and Kirchhoff's law is what? It has to ensure that the thermal equilibrium. Likewise, here I have ensured the local thermal equilibrium. if the local thermal equilibrium is valid, and also the other assumptions is there, that is the medium is non-polarizing, okay, and also the refractive index is constant throughout the medium, then only I can write this J eta is equal to this. Okay. So if you have already forgot about this J eta, you can directly memorize this formula by drawing the analogy from this, that something is being emitted. So how can I get that? Maybe something emissivity into the black body, emissive power at that point. So I don't have any black body emissive power, I have only the radiation intensity. So it will be the black body radiation intensity at that point S into some emissivity or some emission coefficient. Now because the local thermal equilibrium is valid, I can write directly that emission coefficient as my absorption coefficient. So that is how intuitively we can interpret this formula. Okay, this was very important, and I write this as C. Okay, so this was there. Now finally, so please be very focused at this one. Okay, so augmentation by in-scattering, this is very important, and at the same time this is a bit confusing, but I will try to make it simpler for you. Let me have a sip of water. Okay, so augmentation by in-scattering. So again I will consider the same control volume. Let me first draw the control volume. Okay. So again this is ds. Let me, okay, now it is fine. So what is happening is that my radiation ray is moving like this. And what do I mean by like this? I am meaning that my normal here is S cap. Okay. And if I talk about the radiation energy that is going through this control volume, then I have to take this infinitesimal solid angle. So that is maybe d omega. Okay. So this is also actually, I mean, minus, okay. So let me term this also as, okay, minus S cap, fine, clear. So now what is happening is that at this point, at the entry of the control volume, okay, from anywhere energy can come, from this direction, from this direction, from this direction, from this direction. Okay. So in scattering means that how much energy is coming from inside and being scattered in this direction, that is coinciding with the direction of the travelling radiation ray. Okay. So I have to integrate all these contributions from all these directions throughout this hemisphere. So now I will take, okay, now I will take maybe with this color, okay, a separate direction, this, and sorry, no, So this is d omega I solid angle for the incoming radiation ray at the entry point of the control volume, and this is this direction is SI cap. Okay. So here I will write this as, so this blue, okay, this blue thing is nothing but my I eta at a position S, and this violet ray I will term it as I eta I, but that is a function of SI. Okay. So, okay. So now I need to find what? First I need to find how much energy, okay. So let us go, so let us build first a roadmap. So how much energy is coming from direction SI, okay. Then we need to know how much is being scattered inside inside the CV, right. Then I need to know how much is being scattered in S direction within solid angle d omega, okay. Then I need to integrate for all the incoming direction, that is the SI, okay. So I have already told that from every direction that can be some inside, I mean from every direction some ray can come, and that will be contributing for the inscattering part. So first let us find that how much energy is coming from the direction SI. So we are given I eta I SI. So this is, okay, this is the radiation intensity. So to get the energy I need to multiply area, but not the area normal to the ray. How can I find that? That will be SI dot S, okay, that is dA cos theta. Then I need to multiply by the solid angle, then I need to multiply by d eta, okay. So then it is over. So this is the first part, okay. So if I just write this to save time, you will be, I think you are taking the notes also, okay. So this is 1, this is 2, this is 3, this is 4. So this part is the 1. Now this is the total energy incoming. Now how much is being scattered in the CV? So we know that if some ray is incoming, that is if some ray INS is incoming at a position S, then the scattered ray will be into sigma eta S into ds. Now this ds is what? This ds is the distance travelled by this ray, okay. So here do I have to multiply this with ds? Because see, this ray is travelling like this, so it is not covering this distance, it is covering this distance, right. So this distance is what? If this is S, if this is theta, then this will be ds by cos theta, okay. That is the thing. Sorry, if this is ds and this is theta, then this will be ds by cos theta, and cos theta is what? this dot this is what SI dot SI cap, and this is what S cap. So cos theta is SI cap dot S. So this length will be what? ds by SI cap dot S cap, right? So I need to multiply this by what? So INS sigma ns ds, okay, dA, okay, no, not ds. So this part 2 will be this one dA SI dot S, this one I need to multiply with the scattering coefficient and with the ds by SI dot S. So this I can cancel out. Fine. I have found out this part 2. Now 3 is how much is being scattered in S direction within solid angle d omega. So here I will be defining something called the what? Scattering phase function. Phase function, that is phi. Clear? And this is a function of this. So this is defined by this, that the phi is this by 4 pi. This is the fraction of energy, okay, incoming through the direction SI and going, okay, I have to multiply this d omega here also, going in is, or I should write scattered, okay, scattered fraction of energy scattered through, okay, in scattered or scattered through, okay, scattering through the direction SI and scattered into, okay, the low power, the direction S, okay, within d omega. So it is just the fraction of this energy. So it is what? So this is that how much of this energy is going into this control volume, into this direction inside this solid angle, okay. So now that means the answer of part 3, so this will be 3, okay. So that will be here, if I copy this, right, if I copy this and if I make it small, so this will be the answer of part 3. This will be this into phi, that is a function of SI dot a, sorry, comma S by 4 pi into sigma eta S. Clear? Okay. So the last part, integrate for all the incoming direction. So if I integrate for all the incoming direction, so then I will get the actual thing, that is if my d eta and that is in scattering, okay, in scat, okay. So if I have to get the total energy that is being in scattered, I have to multiply with dA, I have to multiply with d eta, okay, and I have to multiply with d omega. So this is the total energy that is being in scattered, okay, in the solid angle this d omega, and also in the direction S cap, that is a function of S cap, okay, and I need to multiply also these areas, okay. And obviously you can argue with me that I should have multiplied this, I mean S cap, but actually this ray is travelling already normal through this area. So this will be S cap dot S cap, and that is 1. Okay. Now this is equal to this whole part. No, not this whole part. I have to integrate, because this is the total energy that is being inscattered through this infinitesimal direction and solid angle. So total energy that is inscattered, that means I have to integrate over the incoming control volume. Okay. So if I do integrate, so this will be integration over the omega I. So this will be from 0 to 4 pi. If I integrate, it will be, let me write. So this will be dA d omega I d eta sigma ns ds phi by 4 pi. Okay. So sigma ns was already there, so I don't need to write it again. Okay. So here this dA is like constant, because the integration is only over this phi I. This is also a constant. Array? Why it is not working? Okay, so I think my charge of the pencil is over. So you can wait for some time. So here you can see I will cancel this d eta and this d omega. I have forgot to write this d omega here. There will be a d omega. Okay. So this will be d omega. I have to write here, because see, this was d omega here. I forgot to write that. Okay. And I will be writing here also the d omega, and I will be cancelling out this d omega here, this d eta here. So I got my required thing, that is my d eta in scattering is equal to, okay, the sigma ns is a constant and 4 pi is also a constant. This will be over 4 pi I eta I si cap d omega I, and what, this will be what, phi, that is a function of, so just for the sake of mathematical cleanliness, I will be writing it like this, into ds. Okay. So okay, into ds will be there, but I can take that ds out also. So this will be actually d omega I, okay, this whole into ds. So this here is right, these parts. Okay. Array. Okay, this here is right. So here I have something into ds, right? See, here also I have something into ds. So those parts are, I mean, almost similar. So I will stop this lecture here. In the next lecture, so this is my equation D. If you have any doubt or any problem understanding any of this attenuation or augmentation, please put that in the comment box. So in the next lecture, I will be combining all these 4 things, and I will be finding that how much is the total change when a radiation is going through a medium, a participating medium. These are the small changes, not small changes, these are the part changes. Now I have to add all these things, I will be finding the total change. Okay. So after that we will be also solving a couple of problems regarding participating media, and after that, if I get time, I will be also solving problems from the chapters that I have already taught. So until that, goodbye, take care, and thank you.